Nothing is permanent in this world but change. This is a cliché statement that is absolute in day-to-day living. All things are constantly changing, including the substances that currently exist. In chemistry, the change in pure substances may happen in two ways. It can be through nuclear reaction, which involves the change in the nucleus or protons and neutrons of an atom, or chemical reaction, which involves the change in the interaction between the electrons in two or more pure substances. In this lesson, we are going to focus on chemical reactions. Chemical reaction is a type of reaction that produces new product from the interaction of two or more pure substances through their valence electrons. However, unlike the nuclear reaction, which may produce new particle or element, the product of a chemical reaction still retains the composition of the original reacting substances or reactants. For example, if sodium and oxygen gas chemically react with each other, it will form a product known as sodium oxide, which is neither a sodium alone nor oxygen gas alone. Nonetheless, undeniably, the original composition of the reactants, sodium and oxygen, are retained in the product. Same thing goes when ammonia and sulfuric acid chemically reacts with each other to form ammonium sulfate. The new product ammonium sulfate retains the overall composition of ammonia and sulfuric acid, that is nitrogen, hydrogen, sulfur and oxygen, but with different atomic arrangement. This clearly differentiates chemical reactions from nuclear reactions. In nuclear reaction, when the nuclei of sodium atom with atomic number of 11, and oxygen atom with atomic number of 8, interact through nuclear fusion, it will not create sodium oxide, but it will create a new particle or element, which is chlorine, with atomic number of 17. The new product, chlorine, is neither sodium nor oxygen, and it does not retain the composition of the original reactants. In fact, there is no more trace of sodium or oxygen in the new product, which absolutely changes the identity of the two reactants. Now, we already know that the term chemical reaction is not a colloquial term that can always be applied to all reacting substances for as long as there is a new product. To discriminate a reaction whether it is a chemical or nuclear reaction, we should therefore consider two things. Number 1, the interacting subatomic particles involved. Does it involve rearrangement or interaction between nuclear particles like protons and neutrons, or does it involve interactions between valence electrons? And number 2, the new product form. Does the reaction formed new particle, element or radiation? Or does the reaction formed compounds or retained its original elemental composition? Having these things in mind, let us further dig deeper on the types of chemical reactions. Chemical reactions are represented through chemical equations. Chemical equation is a shorthand notation of a chemical reaction which shows the reactants and products involved in a reaction. The reactants and product are separated by arrow, and the arrow is read as will yield to, or will produce. For example, the chemical equation shown as read as reaction of sodium and chlorine gas will yield to sodium chloride. Notice that chlorine is written as Cl2, and not Cl alone. Why? It is because, naturally, chlorine atoms are diatomic, meaning, they always exist by pair in nature. Therefore, in chemical equations, isolated chlorine is usually written with 2 as its subscript. This is also true for other diatomic elements like hydrogen or H2, nitrogen or N2, oxygen or O2, fluorine or F2, bromine or Br2 and iodine or I2. There are 5 general classifications of reactions in chemistry. The first type of chemical reaction is known as combination reaction or synthesis. Combination reaction or synthesis is a type of inorganic chemical reaction which involves the union of 2 or more reactants to form one product. Essentially, there are many reactants but only one product in this type of reaction. This reaction follows the format A plus B will yield to AB, where A and B are the reactants and AB is the product. Formation of rusts and other oxides, formation of oxo salts, or salts with oxygen, and formation of acid rain are examples of this reaction. Other examples are exemplified by the reaction of sodium and chlorine gas to produce sodium chloride, reaction of silver oxide and water to produce silver hydroxide, reaction of carbon dioxide and water to produce carbonic acid, reaction of silver oxide and carbon dioxide to produce silver carbonate, and reaction of nitrogen gas and hydrogen gas to create ammonia. As you can see on the examples, there are always many reacting substances, but all of them have only one product, hence, they truly exemplify combination reaction. The second type of chemical reaction is the direct opposite of combination reaction, and that is decomposition reaction or analysis. Decomposition reaction or analysis is a type of inorganic chemical reaction which involves the separation of one reactant to form several products, often through heat. Other ways or things may be applied for the decomposition reaction to occur, such as the application of electricity, or using a catalyst. We are going to discuss catalyst later. Essentially, there is only one reactant, but there are many products in this type of reaction. This reaction follows the format, AB will yield 2A and B, where AB is the only reactant and is considered as one body, while A and B are the products which are separate from each other. Applying electricity to water to form hydrogen and oxygen gases, also known as electrolysis, and decomposition of hydrogen peroxide by using potassium permanganate as a catalyst to form water and oxygen gas, are examples of this reaction. Bear in mind that if you saw a triangle above the arrow in chemical equation, that means the decomposition reaction is done through heat. Other examples of such reaction are exemplified by the decomposition of sodium oxide through heat to produce sodium and oxygen gas. Decomposition of silver carbonate through heat to produce silver oxide and carbon dioxide. Decomposition of silver bicarbonate through heat to produce silver oxide, carbon dioxide and water. Decomposition of sodium bicarbonate through heat to produce sodium carbonate, carbon dioxide and water. And decomposition of sodium chlorate through heat to produce sodium chloride and oxygen gas. As you can see on the examples, there is always one reacting substance for each item, but all of them have many products. Hence, they truly exemplify decomposition reaction. The third type of chemical reaction is known as single displacement reaction or substitution. Single displacement reaction or substitution is a type of inorganic chemical reaction which involves the replacement of one element to a compound. Here, one of the reactants must be a pure element and the other must be a compound. The pure element will replace one of the elements in the compound to which it will react. This reaction follows the format A plus BC will yield to AC plus B, where the element A replaces the element B in the compound BC. Bear in mind that not all the times, an element can replace another element in a compound. Generally, a metal can only substitute another metal, except for hydrogen which can replace and can be replaced with a metal. On the other hand, a non-metal can only replace another non-metal. For example, in the reaction of chlorine gas and sodium bromide, chlorine can only substitute the bromine atom in sodium bromide, but not the sodium, because chlorine is non-metal, while sodium is metal. Substitution reaction is governed by reactivity series. Reactivity series is a chart that shows the arrangement of elements based on their reactivity. In metals, group 1A elements like potassium, sodium and lithium are the most reactive ones, while elements like silver, gold and platinum are the least reactive metals. In non-metals, fluorine is the most reactive element, while phosphorus is less reactive as compared to other non-metals in the reactivity series chart. In substitution reaction, generally, if the replacing element is more reactive than the element that it will replace, then substitution reaction may occur. For example, if sodium interacts with magnesium chloride, sodium can replace magnesium to produce magnesium and sodium chloride, since sodium is more reactive than magnesium. However, if the replacing element is less reactive than the element that it will replace, then there will be no reaction. For example, the interaction of zinc and magnesium chloride will yield no reaction, because zinc is less reactive than magnesium. Therefore, zinc cannot kick the magnesium out of magnesium chloride. Another example is the interaction of calcium bromide and fluorine gas. Since fluorine is more reactive than bromine, then it can replace the bromine in calcium bromide, producing calcium fluoride and bromine gas. Also, as mentioned earlier, hydrogen is the only non-metal that can replace and can be replaced with a metal. However, there are some rules that must still be observed here. Elements like potassium, sodium, lithium, barium, strontium and calcium can replace hydrogen even in normal water, but they can also replace hydrogen in acids. On the other hand, elements like magnesium, aluminum, manganese, zinc, chromium, iron, cadmium, cobalt, nickel, tin and lead can replace hydrogen in acids, but not the hydrogen in normal water. For example, the interaction of aluminum and water will yield no reaction since aluminum can only replace hydrogen in acids, but not hydrogen in water. However, the interaction between lithium and water will yield to lithium oxide and hydrogen gas, since lithium can replace hydrogen both in normal water and in acids. Harvesting pure silver from the reaction of silver nitrate and copper exemplifies this reaction. In such reaction, since according to reactivity series chart, copper is more reactive than silver, then copper can replace silver in silver nitrate, yielding pure silver and copper nitrate. As shown in this video, the crystals growing from the wire are the pure silver crystals. Other examples of such reaction are exemplified by the substitution of lithium and zinc sulfate to produce lithium sulfate and zinc, substitution of barium and sulfuric acid to produce barium sulfate and hydrogen gas, and the substitution of chlorine gas and ammonium iodide to produce ammonium chloride and iodine gas. The fourth type of reaction is the double displacement reaction, which is also known as metathesis. Double displacement reaction or metathesis involves the exchange of ions between two compounds. Here, the two reactants are both compounds, and they exchange their ions to form two new products. This reaction follows the general pattern AB plus CD will yield to CB plus AD, where AB and CD are the reactants, while CB and AD are the products. For example, when sodium chloride and silver nitrate react with each other, they will produce silver chloride and sodium nitrate. In such reaction, sodium, which is the ion A, and silver, which is the ion C, exchanged in position. Now, when a metathesis produces two substances, where one is soluble to water, while the other one is not, then the double displacement reaction is known as precipitation reaction. This is true in the reaction of potassium iodide and silver nitrate, which will yield to silver iodide and potassium nitrate. Silver iodide is not soluble to water, while potassium nitrate is soluble to water. However, when a metathesis involves the reaction between an Arrhenius acid and an Arrhenius base, the decomposition reaction will be known as neutralization reaction. Arrhenius acids are acids with hydrogen ion as its cation, such as the hydrochloric acid, sulfuric acid and perchloric acid. The chemical formulas of these acids conventionally start with hydrogen ion. On the other hand, Arrhenius bases are bases with hydroxide ion or OH as its anion, such as the magnesium hydroxide, potassium hydroxide and rubidium hydroxide. The chemical formulas of these bases conventionally end with hydroxide ion. An example of neutralization reaction occurs when hydrochloric acid and sodium hydroxide react with each other to form sodium chloride and water. The final products of traditional neutralization reaction are always salt and water, which are neither acids nor bases. Volcano experiment is yet another example of double displacement reaction. In such experiment, baking soda or sodium bicarbonate reacts with the acetic acid in vinegar to form carbonic acid and sodium acetate. The carbonic acid further undergoes decomposition reaction to produce carbon dioxide and water. Other examples of double displacement reaction include the reaction of sodium chloride and silver nitrate to yield sodium nitrate and silver chloride, the reaction of sulfuric acid and potassium hydroxide to yield water and potassium sulfate, and the reaction of barium chloride and potassium phosphate to yield barium phosphate and potassium chloride. The fifth and last general classification of chemical reaction is known as combustion reaction. Unlike the first four types discussed in this video which occur in inorganic compounds, combustion reaction is an organic reaction. To be specific, it involves the reaction of an organic compound to oxygen gas to produce carbon dioxide, water, and energy or heat. Organic compounds are carbon-containing compounds, where their carbon atom or atoms are all linked to other nonmetallic elements via covalent bond. Alcohols, sugars, proteins, diesel, oils, rubbers, and plastics are some examples of organic compounds. All combustion reactions are considered exothermic reactions, meaning it produces a lot of heat. The amount of heat that will be generated after the chemical reaction surpasses the amount of heat that will be used to start the reaction. Combustion reaction follows the pattern organic compound plus oxygen gas will yield to carbon dioxide, water, and energy or heat. Bear in mind that aside from the mentioned products, other products may also be produced during a combustion reaction, especially if the organic compound has other elements, aside from carbon, hydrogen and oxygen. However, primarily, all combustion reactions have carbon dioxide, water, and energy or heat as their main products. One example of combustion reaction is aerobic cellular respiration. Aerobic cellular respiration is the process that is used by many living organisms to produce energy through the food that they eat. Essentially, in this process, the glucose, an organic sugar with a chemical formula of C6H12O6, reacts with oxygen gas to produce carbon dioxide, water, and energy. Here, glucose will come from the food that we eat, while oxygen gas will come from the air that we inhale. On the other hand, the carbon dioxide produced in the process will go out of our body through exhalation. Another example of combustion reaction is the combustion of diesel in car's engine. Diesel is a mixture of different organic solvents, one of which is decane, with a chemical formula of C10H22. When the decane in diesel is internally combusted, or reacts with oxygen gas, it will generate carbon dioxide, water, and energy. The energy produced in the process will be used by the car for it to operate. Note that, in this reaction, other products may also be formed if the diesel has other elements aside from carbon, hydrogen, and oxygen. Those are the 5 general classifications of chemical reactions. There are several evidences of the occurrence of chemical reaction, one of which is explosion, which is mostly accompanied by evolution of gases. For example, the dynamite that was invented by Alfred Nobel in 1866 primarily contained nitroglycerin, which when ignited, will explode violently, and will decompose into several gases like carbon dioxide, water, nitrogen gas and oxygen gas. Such reaction is a decomposition reaction. Another evidence of chemical reaction can be seen when sodium bicarbonate reacts with acetic acid through double displacement reaction. In such reaction, which ultimately produced carbon dioxide, water, and sodium acetate, the most prominent evidence that can be observed is the formation of bubbles. Bubbling and fizzing are another evidences of chemical reaction. Food spoilage is another event that shows some evidences of chemical reactions. The change in smell and taste of something may also indicate the occurrence of chemical reaction. Reaction of some metals to atmospheric oxygen through combination reaction to produce softer and duller metal oxide shows 2 primary evidences of reaction, and those are corrosion and color change. Corrosion may be in the form of rust, patina, or tarnish. For example, the Statue of Liberty is one of the famous sculptures that has a patina all over its body. This is because the Statue of Liberty is primarily made of copper, and over time, the copper atoms in the statue have reacted to atmospheric oxygen, producing the greenish patina of copper oxide. The original brassy brown color of Statue of Liberty in 1885 have therefore changed into a greenish one, suggesting that its copper content had oxidized. Formation of precipitate is another evidence of chemical reaction. Precipitates are any products in chemical reaction that are not soluble to water. For example, In the double displacement reaction of sodium chloride and silver nitrate, the products are silver chloride and sodium nitrate. Silver chloride is not soluble to water, therefore, upon reaction, it will just precipitate out of the solution. Finally, flame and light production can also be observed as another evidence of chemical reaction. This can be seen when magnesium ribbon is ignited, to react with atmospheric oxygen. The reaction produces a white sediment of magnesium oxide, but upon reaction, bright flame and light are produced. There are 5 primary factors that affect the rate or speed of chemical reaction, and these are the temperature, pressure, presence of catalyst, surface area of reactants, and concentration of the reactants. Temperature is directly proportional to the rate of chemical reaction. This is because, increasing the temperature also means increasing the kinetic energy of the molecules in a reaction. An increase in kinetic energy would make atoms move faster. When atoms move faster, the chance of collision between molecules is very high. High collision rate enables molecules to bump to each other, and produce new substances. For example, under normal temperature, ammonium nitrate does not undergo decomposition reaction. However, if we increase the temperature of the environment to where the ammonium nitrate is stored, the molecules of ammonium nitrate would start to move faster, until it decomposes into nitrous oxide and water. Such reaction would create tremendous amount of energy in the form of explosion. The decomposition of ammonium nitrate was the alleged reason behind the explosion that happened in Beirut, Lebanon on August 4, 2020. Unfortunately, the event caused 218 deaths and, approximately, 7,000 injuries. Pressure is another factor that may affect the rate of chemical reaction. Generally, pressure does not affect the reactions which involve liquids and solids. However, gaseous reactions are greatly affected by it. In any gaseous reactions, as pressure increases, the speed of chemical reaction also increases. For example, under standard atmospheric temperature and pressure, nitrogen gas and hydrogen gas do not react with each other. However, in the first decade of 20th century, German chemists Fritz Haber and Karl Bosch invented the Haber-Bosch process. In such process, Haber and Bosch subjected the nitrogen gas and hydrogen gas under high temperature and pressure, and with the use of a metal catalyst. Such method was able to synthesize ammonia from the combination reaction of nitrogen and hydrogen gases. This process revolutionized the agriculture in the 20th century, as it initiated the production of artificial fertilizers. Unfortunately, during the World War I, the synthetic ammonia from Haber-Bosch process were also used by Germany to create nitric acid, which is the precursor of nitrates in explosives. The third factor that may affect the rate of chemical reaction is the presence of catalyst. Catalysts are any chemicals that can speed up chemical reactions without consuming itself, or without having a net change on its composition. Since there is no net change in the composition of the catalysts, they are not considered part of the products in chemical reaction. Catalysts work by lowering the activation energy of a reaction. Activation energy is the energy required for the chemical reaction to occur. Without the catalyst, a reaction may be naturally slow because it needs to meet or surpass the activation energy. However, with the presence of a catalyst, the activation energy is lowered down, and so the reactants can react faster. In our body, enzymes act as our natural biological catalyst. Through different enzymes, many important chemical reactions inside our body happen immediately, such as the digestion of food and cellular respiration. In plants, they also need enzymes to do the photosynthesis. All organisms need catalysts. Without these biological catalysts, there would be no life on Earth. The fourth factor that may affect the rate of chemical reaction is the surface area of the reactants. Generally, surface area is directly proportional to the rate of chemical reaction. In chemical reaction, surface area is the total area of a substance that is exposed in external environment. This area would readily react with other chemicals, as compared to the hidden or unexposed areas. Therefore, increasing the surface area, or the exposed parts of a substance, is directly proportional to the rate of chemical reaction. For example, compacted block of a substance would react slower than its powder form, because powders have more areas exposed to the reactants than solid blocks. This is the reason why gas is the most reactive phase of a matter, as gas molecules are not compacted, and they have already achieved the maximum surface area that can be exposed to other chemicals to cause reaction. Finally, the concentration of the reactants also affects the rate of chemical reaction. Generally, as the concentration of the reactants increases, the rate of chemical reaction also increases. This is because, when the concentration of all the reactants increases, more molecules or ions interact to form new compounds. For example, the reaction of copper and nitric acid, which produces copper nitrate, nitrogen dioxide, and water, may happen at faster rate if nitric acid is in its pure concentrated form, or it is not diluted in water, such as the one that is shown in the video. These are some of the basic concepts about chemical reactions. Thank you very much for watching, and have a nice day.